Okay, welcome back to another video lecture for calculus. And in this section, section 2.3, we're going to be discussing Lagrange's mean value theorem and a special case of the mean value theorem called Rolle's theorem. And we're actually going to start with a special case first because it's one of the more important results that we use in the sections after this one. And I think that once you see how this works in the Rolle's theorem case, then it will make sense for the mean value theorem as well. So the statement of Rolle's theorem is just this right here. It says that if f is a function that is continuous over a closed interval a to b, and it's differentiable on the open interval a to b, so that the difference between f of a and f of b is 0, then there exists a c in between a and b, so that f prime of c is equal to 0. So let's break down what this theorem says, and then we can look at a example and generalize it to the mean value theorem. So all that the continuous part of this theorem says is that if you include the endpoints in the drawing that you make, so you have like this point here and this point here, and we'll let this one equal to x equal to a and this one to x equal to b. And if we draw some line in between the two, maybe like that, I do not have to pick up my pencil in order to draw that line. That's all that continuous part means. It just says that there's no breaks in the domain of this function between a and b. That's it. The second part says differentiable on the open interval a to b. So the open interval means if you ignore these two endpoints, and the reason for that is that at the endpoints you will not always be able to calculate a derivative because you don't know what happens necessarily in some cases on either side of a and b. So we get to ignore the endpoints for this one. That's actually a good thing. So for everywhere else on this function, am I able to calculate a derivative? Now in the previous section, what we talked about was how the derivative represents the slope of a function at all the different possible x values. It's basically a function that describes the slope of another function. And in the case of polynomials, derivatives are of a lower power. As we learned in Unit 1, every time we do a derivative, it reduces the power of the polynomial. So the derivative of something like this, which is an x squared function, will have like a straight line as its derivative. It would be like a y equals to x equation. So if we're able to calculate a slope along this thing everywhere, in other words, I don't have any places where I wouldn't be able to necessarily state exactly what the slope is. And furthermore, the slope won't be undefined anywhere. And an undefined slope is just like a straight up and down slope like that. So you can think about what kinds of things would disqualify functions from being differentiable, but the idea is if I can calculate a derivative along this line at all the points, then it is differentiable between the open interval a to b. And remember, we ignore the endpoints when we compute if it's differentiable. The last part says, so that f of a minus f of b has to equal 0. What that means is that f of a has to be the exact same thing as f of b. In other words, the place that these two dots happen along the y-axis must be in the exact same spot. In other words, if I take this yellow color here and I draw a line straight across, the slope of that line has to be 0. That's what the last part of the theorem says. So notice that the slope that I've done with this yellow line uses 2 points to calculate the slope. It's f of b minus f of a. And so what we have is actually a slope of a secant line at a point on this curve. So the last part of this just tells us that if we can find a place where the secant line slope is equal to 0, then there is a place somewhere along this curve in between a and b where the tangent line slope is equal to 0. And a tangent line, if we recall from the previous section, is just a line that crosses this curve in precisely one place, right there. So what the theorem really says is that if you can show that there's a specific place along a function where the secant line is equal, the slope of the secant line is equal to 0, then there must be a place where the slope of the tangent line is equal to 0. And so some interesting things to note here, just as observations, you notice that when we use a simple case like a parabola, then this tangent line corresponds to the vertex point at the bottom. And the same thing would be true if I were to flip this thing over. Some other observations, you notice that this C value with the x coordinate of whatever that point is in fact in between A and B, exactly as the theorem states. And excuse me. The reason why this is important is that it can be helpful in identifying specific features of a graph. And furthermore, this theorem actually tells us how to find extremums of our graph. In other words, how to find special features of the graph using derivatives to do so. So remember that f prime, the first derivative, is just the slope of a tangent line across our curve. And what we're doing is we're hinting at the existence of a specific place where the slope of that tangent line must equal to 0. Okay, so it's actually very easy to change this theorem into the mean value theorem. So Rolle's theorem is this specific case where we have this line that says f of A minus f of B must equal to 0. The mean value theorem has all the same conditions. We're just going to change this part about where it has to equal to 0. And the mean value theorem just says if we have a certain secant line on our graph and we can calculate its slope, then somewhere along the graph, the tangent line will also have the same slope as the secant line. And this one should be pretty easy to see. You notice that the secant line here, the slope was 0, and so the tangent line slope must equal 0. But all that the mean value theorem does, the only change that it really makes, is it allows us to look at functions in a way where the endpoints that I've chosen, A and B, do not have to be along the same horizontal line to each other. In other words, all the mean value theorem does differently than Rolle's theorem is it takes this secant line and it allows for it to have positive or negative slope. So here you can see that the yellow line is drawn with positive slope because A is lower than B, and so to go from A to B, we must go up that amount. Hence, we end up with a positive slope. And if we look for sort of a specific place along here, there is such a place that I can find where I can draw a tangent line that has parallel slope to the secant line. And we'll kind of always be able to play that game, and that's basically what the statement of Lagrange's mean value theorem is. Now, if you understand Rolle's theorem, then you understand all that you need to for the next section where we're going to begin talking about the extremums of graphs. Now, mean value theorem is important because it's used a lot in several constructive proofs in upper level mathematics. And so we always show the mean value theorem, but the specific case that we're worried about in Calculus 1 is the case where f of A minus f of B is precisely 0. In other words, specifically Rolle's theorem, which you can think of as just the little brother of the mean value theorem.